Hello, welcome to Mickey Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement for creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Prandtl, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers for their continuous support and encouragement. Today's topic of interest is dimensionless numbers. Dimensionless numbers are the numbers which used to find the properties of different applications. For an example, if an aeroplane is flying, we are indicating in the speed of a flight in a Mach number how it is being wrote, like that we are going to give. And similarly, if we are constructing, we are trying to constructing a hydroelectric power plant, we are using pressure force, so Euler number is very important. Similarly, for the conduction and heat transfer problem, the dimensionless numbers plays a vital role of finding the different properties. If it is a fin, if I am having an engine, I am trying to establish an air cooling system. There we are designing a fin material, how it look like, how the conduction or convection is being transferred, so that we have to know. Similarly, how the buoyancy force of a system, of a surrounding, will help us to transfer or conduct a heat, that you have to know. Similarly, Nusselt number is there, Rayleigh number is there, Prandtl number is there, Stanton number is there. So like that, for heat transfer as well as the flow through, the fluid flow through, we are using different numbers of dimensionless numbers. Now we are going to discuss those numbers in detail. So here, the dimensionless numbers and their applications. First one is the Reynolds number. Reynolds number is the ratio of inertia force to inertia force to viscous force. Inertia force to viscous force is called Reynolds number. If the Reynolds number if the Reynolds number is less than 2000, then it is said to be laminar flow. If the Reynolds number is more than 4000, it is known as a turbulent flow. If it is in between 2000 and 4000, it is a transitional flow. Transitional flow. Like that, in the flow through pipes, with the help of the Reynolds number, we can find whether the flow is in a laminar or turbulent, whether the viscous dominant or eddy dominant, we can easily find. For finding these things, we are using the Reynolds number. What happen if the flow is viscous? What happen if the flow is turbulent? The shear stress and the velocity distribution is being varied for this type of a flow. If the shear stress is varied and velocity is varying, the flow is being different. The flow property is being different. Next one is the Froude number. Froude number, Froude number is the ratio of inertia force to gravity force. Inertia force to gravity force. This Froude number is used in hydraulic jumps. When open channel flow, if the flow is said to be an open channel, we can use this Froude number. We can use the Froude number. The in open channel, water surfaces are being waved and similarly water is being flowed. Therefore, the water surface velocity to the wave velocity is the definition of the Froude number. And similarly, if the Froude number is less than 1, it is said to be a subcritical flow. If the Froude number is equal to 1, this is called critical flow. If Froude number is greater than 1, this is called supercritical flow. Supercritical flow. Like that, the flow is being, for the open channel flow, it is being differ. It used to govern the strength of the hydraulic jump. Used to define or govern the hydraulic jump. Okay, next one is the Weber number. So Weber number is defined as the uh, Weber number is defined as the square root of inertia force to the surface tension force. It is the square root of inertia force to the surface tension force. It is used in capillary effects. It is used in capillary effects. Next is a Euler flow. Euler flow is defined as the square root of inertia force to the pressure force. Inertia force to the pressure force. In like the hydraulic structures, building a hydroelectric power plant, or like to transfer, we are liking to transfer a water from a dam to somewhere to some of the villages. We are using a huge pipe. What happens if the pipe is suddenly closed? It produces a pressure waves that is called water hammer. So in order to measure the water hammer, we are using this Euler flow, Euler number. Not only for the water, if we are liking to transfer a petroleum product or a gas or an oil, we are using the Euler flow in order to make sure that the pipe will not burst at any cost. For that purpose, the Euler number is being used. And similarly, Mach number. Mach number is the ratio of square root of inertia force to the elastic force. In aeroplanes, rocket propulsions, all the things, we are using the Mach number. If the Mach number is less than 1, it is called subsonic flow. If Mach number is equal to 1, that is called the sonic flow. If Mach number is up to 1 to 3, it is called supersonic flow. Like that, 1 to 5, 3 to 5, it is called hypersonic flow. And between 2.5 to 4, it is called transonic flow. Like that, different types of the flows is being used, not only for the aeroplanes and also for the submarines. We can use this Mach number. Okay, I hope you have understand the dimensionless numbers, and also for finding the compressible or incompressible flow, Mach number is being used. Mach number is the ratio of the square root of inertia force to the elastic force. So in order to find whether the flow is compressible or incompressible, we can use Mach number. And free surface flow, Weber number. Pipe flow, it is Reynolds number. Boundary layer flow, it is a skin friction coefficient. And Froude number, it is for governing the strength of the hydraulic jump, and it is defined as the inertia force to the gravity force. Make sure that it is the square root of inertia force to the gravity force. So water surface velocity to the wave velocity is another formula for finding the Froude number. If Froude number is less than 1, it is called subcritical. If it is equal to 1, it is critical. If it is greater than 1, it is called supercritical. So with this, the dimensionless numbers in the fluid mechanics is being over. So these dimensionless numbers are governed for finding the fluid properties. The next is the for heat conduction. For heat convection, we are using Nusselt number. For heat convection, we are using Nusselt number, that is convecting the ratio of the Nusselt number is the ratio of convective heat transfer to the conductive heat transfer, heat exchange, we can say convective heat exchange to the convective heat exchange to the conductive heat exchange. So that is called Nusselt number. And similarly the Biot number, it is for lumped heat transfer, for measuring a lumped heat transfer. So internal conductive resistance to the external conductive resistance is the ratio. The Biot number is the ratio of internal conductive resistance to the external convective resistance. So that is called, we say it Biot number. So Biot number, which is HL by K. Similarly Nusselt number is also HL by K, where it is for reflectivity, it is for resistance, it is R for resistance. Here it is convective heat transfer, it is based on transfer, it is based on resistance. You can notice this. And Biot number, it is for Biot number is for solids, and Nusselt number is for liquids. For liquid flows, we are using Biot numbers. Sorry, Nusselt number. For solid, the conduction and convection, we are using Biot number. Okay, and next is the Fourier number. Fourier number is also called as a dimensionless time term. It is the ratio of heat conduction to the rate of internal energy. It is the ratio of heat conduction to the rate of internal energy. The Froude number is equal to alpha T by L square. Alpha T by L square. Next is a Grashoff law. Grashoff law is the ratio of buoyancy force to the viscous force. Grashoff number is the ratio of buoyancy force to the viscous force. We can say G beta into Ts minus TL into L cube divided by mu square. We can say instead of mu is, we know that mu is the dynamic viscosity. So mu by rho is called nu. This is kinematic viscosity. So instead of this, we can use G into rho square beta and Ts minus T infinity into L cube whole divided by mu square. Like that we can also put an equation. Next is the Nusselt number. Nusselt number is the ratio of convection heat transfer to the conduction heat transfer. And next is the Peclet number. Peclet number is the product of Reynolds number and Prandtl number. Peclet number is the ratio of Reynolds number and Prandtl number. Prandtl number is the ratio of the kinetic viscosity to the thermal diffusivity, or molar diffusivity to the thermal diffusivity, we can say in two types. Prandtl number is the ratio of kinematic viscosity to the thermal diffusivity, or we can say molar diffusivity by thermal diffusivity. We know that Prandtl number is equal to mu Cp by K, and similarly Prandtl number is equal to cube root of molar diffusivity to the thermal diffusivity. Molar diffusivity to the thermal diffusivity. So this is the formula. So instead of this, we can use PR power 1 by 3 is equal to delta by delta T, whereas PR is equal to mu Cp by K. Mu Cp by K, like that we can say. And next one is the Rayleigh number. Rayleigh number is the product of Grashoff number to the Prandtl number. Grashoff number to the Prandtl number. And Reynolds number, we know that inertia force to the viscous force, that is UL by mu. And next one is the Stanton number. Stanton number is used to measure heat transfer coefficient. It is used to measure heat transfer coefficient. It is the ratio of Nusselt number to the uh, Nusselt number to the Peclet number. So Stanton number is the ratio of Nusselt number to the Peclet number, where Peclet number is equal to Reynolds number into Prandtl number. So like that we can use this Nusselt number. And I'm going to discuss some detail about this Nusselt and the Peclet number. The Nusselt number is equal to Nu is equal to HL by K. For the constant heat flux, Nusselt number is equal to 4.36. For constant wall temperature, Nu is equal to 3.66. And similarly, the Biot number, it is for solids and Nusselt number is for liquids. So this term we can remember by means of the BSNL. That term, the well-known mobile well-known tower government tower, the BSNL. So Biot number for solids, Nusselt number for the liquids. So we can remember using the BSNL. And here the Nusselt number for the Reynolds flow, for the laminar flow, Nusselt number for the laminar flow, Nusselt number is equal to Reynolds number power 1 by 3 into Prandtl number power 1 by 3. So Nusselt number is equal to the product of Reynolds number into Prandtl number. So Reynolds number power 1 by 2, Prandtl number power 1 by 3. And for turbulent flow for cooling, Nusselt number is equal to Reynolds number power 4 by 3 and Prandtl number power 1 by 3. For heating, turbulent flow heating, Nusselt number is equal to Reynolds number power 4 by 3 and Prandtl number power 2 by 3. And here you can compare this Nusselt number and Biot number formula. Both are same, where Nusselt number is for liquids, Biot number is for solids. So this you have to remember. And for the Prandtl number, we know that Prandtl number is mu Cp by K. If Prandtl number is equal to 1, your molar diffusivity and thermal diffusivity are same. If Prandtl number is greater than 1, then molar diffusivity is more than thermal diffusivity. And similarly, for the Prandtl number is less than 1, this molar diffusivity is less than thermal diffusivity. And we know that for getting for ease of remember, Grashoff number is equal to G into rho into B into rho into del T into L cube divided by this is mu square. And Rayleigh number is the product of Grashoff number and Prandtl number, and Peclet number is the Reynolds number and Prandtl number. So grape juice is for Rayleigh and representative it is for Peclet. So with this I am closing the today's session of dimensionless numbers. I hope you have enjoyed the content which I have delivered. If you have any doubts, please let me know in the comment section and I will put in another video for clarifying your doubts. So until bye bye and thank you from Santhosh. Thank you.